Oh, okay. So let's look at an example on mixing problem. It reads like a 1000 gallon holding tank, a 1000 gallon holding tank that catches runoff from some chemical processes initially has 800 gallons. 800 gallons of water. Initially has 800 gallons of water. Initially. So let's say the initial volume V0 is equals to 800, and then capacity of the whole tank is equals to 1000. Okay, with 2 ounces of pollution dissolved in it. So let's say the concentration of some substance, 2 ounces of that, so concentration in is equals to 2. Polluted water flows into the tank at a rate of, so inflow rate is equals to 3 gallons per hour and contains 5 ounces per gallon of pollution in it. So concentration in is equals to 5 ounces or something like that. Yes, 5 ounces. Now okay, when the amount of pollution, a well mixed solution leaves the tank at 3 gallons per well. So what is entering is 3 gallons, and what is going out is also 3 gallons per hour. But this one here is the initial amount of substance in the tank. So we can say that A naught is equals to 2, or in other words, at t equals to 0, the amount of substance of 0 will be equals to 2, like this. Now the concentration in is 5, the outflow rate is also 3 gallons per hour. It's also 3 gallons per hour. And then the okay, so the concentration out, we don't know. That one we don't know. So C out is equals to question mark. We don't know that one. So this is one part of the question. This question is actually in two folds. The other part will also start from here going. So this is the second part of the question, which we will look at very soon. But let's look at the first part. We know that the differential equation modeling mixing problem is given by the A, the T goes to rate in minus rate out, like this. But we know that rate in is equals to the concentration in times inflow rate. Inflow rate. Now the concentration in was 5, so 5 times the inflow is 3, times 3, and this one you get 15. Now the rate out is equals to C out, that's concentration out, times outflow, outflow rate times outflow rate. But concentration, in other words, the amount of substance in a tank is given by, and concentration is given by the amount of substance over the volume. Okay, over the volume. Now, the amount of substance which we don't know, so we can say A all over the volume. If you realize, they said there was some 800 initially, so there was some 800 initially. In fact, this one is given by V plus change in rate times T. Okay, change in rate meaning the water entering and the water going out. The one entering minus the one going out is the change in the rate of the water times the time. So the initial volume is 800 plus the change in the rate. The water coming in was 3 gallons per hour, so 3, and the one going out is also 3, so minus 3. So this is the change times T, and this becomes A over 800. This minus this is 0. 0 times T is 0. So 800 like this, plus 0T, and this is just A over 800 like this. Now, this is our concentration out. This is the concentration out. This one is the concentration out. But we need to get the rate out, we need to multiply it by outflow. Now the outflow, so now we can then write rate out is equals to C out, which is this, times the outflow, and this becomes A over 800 times the outflow, which is also 3. So this becomes 3A all over 800. So this is the rate out. So now we can then write our differential modeling. So we can write this, the A, the T goes to the rate in. The rate in is 15, which we calculated here. 15 minus the rate out, which is now this 3A all over 800. Now, if you go back to the question, they said something. They said, okay, so chemical process initially has 800 gallons of water with 2 ounces of pollution dissolved in it. It means that our A of 0 is equals to 2. So that is the amount of substance polluted in the water initially. It's just 2. So at time equals 0, the amount of substance was 2. So this is one part, the first IVP. So this is one part of the question, so for which we can then solve this one. Okay, so now let's try to solve this particular differential equation with the given condition. So we have the A, the T equals to 15 minus 3A all over 800, and this will imply we have the A, the T plus 3 over 800A equals to 15 like this. So this one we can solve by the method of integrating factor. This is our P, this is our Q, so we can write mu of T equals to e power the integral of 3 over 800 dt, and when you do this you get e power 3 over 800 t like this. Okay, this is our integrating factor. So we then write the amount of substance for the first part. So we have A of t to be equals to the integral of the Q of T. What is Q of T? 15. So 15 times the integrating factor, which is e power 3 over 800 T plus C, all this over the integrating factor, which is this 3 over 800 T, like this. So integrating this part, we just have 15 times 800 over 3 e power 3 over 800 T plus C all over e power 3 over 800 T, like this. So this one is of 1, this one here you get 5, and 5 times 8, that's 40. So we have 4,000. Sorry, this will go, but this is dividing here, this is dividing here. So obviously this e will not be there again. We just have 4,000 plus C e power negative 3 over 800 T. This is our A of T. This is our A of T. So right now we have A of T here, but we're given that A of 0 is equals to 2. So which we just have to apply to find this C here. So A of 0 to be equals to 4,000 plus C e power negative 3 over 800 times 0 all equals to 2, like this. And so solving this, we have C e power 0, but this is just 0, equals to 2 minus 4,000, and this goes negative 3,998. And so rewriting our model function, we have A of T to be equals to 4,000 minus 3,998 e power negative 3 over 800 T. So this is our model. This is our model. But let's go back to the question and read it again. So we have solved the first part of the question. Let's go back to it and read again and continue with the rest. When the amount of pollution in the holding tank reaches 500 ounces, so the amount reaches 500 ounces, the inflow of the water is cut off. The inflow of the polluted water is cut off. Okay. So it means now fresh water is going in. Okay. Fresh water is going in. So it means that one we don't actually know. That part didn't start from time equals to 0. So that one we have to write a different IVP for it. We have the A, the T for that part to be equals to, now the same thing, we know that rate in minus rate out, and then that particular one, okay, let me just call this maybe A1. So okay, so let me call this maybe the A, maybe okay, let me just leave this time, but we'll be able to distinguish them. So the A of the time here, maybe let me just call this maybe T, maybe T A or something, TA equals to 500 ounces, because when the time reaches this, the pollution in it becomes this. Now let's find our R in, the rate in. Of course, let's go back to the question. We know that rate in is concentration in times inflow rate. Now the concentration in the concentration in they said the ounces, I'm coming, 500 ounces of inflow water is cut off, and fresh water will be entering. Fresh water enters the tank at a decreased rate of this, while the outflow is increased to this. Okay. So fresh water enters at a decreased rate of this. Okay. So the inflow is this, the outflow is this. Okay. So but remember, it is fresh water. So the concentration in this fresh water is 0 because there is nothing inside. It's fresh water, there is no pollution. So it simply means that because this one is concentration in times inflow. Okay. So the concentration in the fresh water will be 0 times the inflow is it is going at a decreased rate of 2, so that is just 0. Okay. Now the rate out, we know that one too is concentration out times outflow. Okay. Concentration out times outflow. Now the concentration out, C out, in other words C of T, will be equals to the amount, okay, the amount over the amount that is in it now, over, we have some water inside already, so 800 plus the change in the rate. What is going in at that time was 2, and what is going out was 4, all that times T. Okay. But here, remember, here our time looks like this. Let me draw this number line. So when we started, this was T equals 0. So we got to some point, T of A. Okay. And then the whole thing is T. And maybe let me say here is T. Now, this is an interval. So T of 0 is less or equal to T of A. Okay. And then this one too is less or equals to T. Okay. Now, what will be this time from here coming here? From here coming here will just be T minus TA, like this. Okay. So, and then the difference here will just, but this one was 0, so the difference here will just be this one. Okay. So right now it means that we cannot write this like this, because we want to write the time, and the time will now be this. Okay. So multiplying this by T minus T E, like this. So let's see. So now we have this equals to A all over 800 minus 2 to brackets T minus T of A, like this. But our rate out is equals to R out now equals to A all over 800 minus 2 into brackets T minus T of A times the outflow. The outflow was 4. And so if we simplify, you get 4A all over 800 minus 2 T minus T of A, like this. But then we can then write our differential modeling equation like dA dt equals to the rate in, that was 0, minus the rate out, 4A all over 800 minus 2 into brackets t minus t of a, like this. And so this simplifies to become 2a negative 2a all over 400 minus t minus t of a, like this. So but we don't know what t of a is. But we reached t of a when we started doing the fresh water was coming in. So it means that we can use the previous solution of the first IVP to find t of a, because when it reaches t of a for that particular one, then the fresh water will start, and then we have an ounces. We have some 500 ounces at that particular time. Don't mind this one. Let's proceed. So right now, so we know that we now have the A. Let me write the A1 of the T equals to sorry, let me just write this. The first IVP was I think 15 minus I think 3A over 800. That one, A of 0 was equals to 2. So the second IVP, so this IVP1, IVP2, the second IVP will now be the A1 dt equals to negative 4A all over 800 minus 2 into brackets t minus t of A, like this. And then we have A of t of A equals to 500 ounces. Good. Now when we solve this, we had A of t equals to 4000 minus 3998 e power negative 3 over 800 t. Okay. Now when the time reaches t of A, the ounces became this. So it means this one will be equals to this. So we can use this model to find the t of A here. Okay. And so now at t equals t of A, we have A of t of A to be equal to 500. This is how it is. So right now we A of t of A equals to 4000 minus 3998 e power 53 over 800 t equals to 500. So this will imply that, sorry, this one will be t of A. So we have negative 3998 e power negative 3 over 800 t of A equals to 500. Sorry, 500 minus 4000, and this implies that we have negative 3998 e power 53 over 800 t of A equals to negative 3500. So we have e power negative 3 over 800 t equals to negative 3500 over negative 3998. And so solving for t, we just take ln of both sides. This and this will go. So we take ln of e power 3 over 800 t a equals to ln of 3500 over 3998, like this. And so this here will come down, this one will come down, and negative 3 over 800 t of A equals to ln of 3500 3998. And so solving for t of A will be equals to ln of 3500 over 3998 divided by negative 3 over 800. And so this becomes 35.5 35.48 hours. So at 35.48 hours, we have 500 ounces. Okay, so right now we can then go back. Okay, we can then write the IVP, which will now be the A1 dt equals to negative 4A all over 800 minus 2 into brackets T minus 35.48 like this. Then at A of 35.48 we have 500 ounces like this. Okay, so we then have to solve this particular differential, this IVP here. We have to solve it. So now let's see, this will be A1. So we have the A1 dt equals to negative 4 A1 then 800 minus 2 brackets T minus 35.48, and so this becomes 2 here will factorize out and cancel this, so we'll get negative 2 A1 all over 400 minus T plus 35.48, and so we'll get negative 2 A1 all over 435.48 minus T. So we have to then solve this. The A1 dt is equals to negative 2 A1 all over 435.48 minus T like this. Now we have this particular thing here, which we can solve by separating the variables. So this will imply we have the A1 all over A1 equals to negative 2 over 435.48 minus T dt. Solving, if we solve, this will imply ln A1 is equals to okay, so if we factorize these two out, we get negative 1 here, up here, and when we differentiate that down here, get negative 1. So that will just be 2 ln 435.48 minus T plus, let me say ln C, that's the constant of integration. So we can rewrite this one as A1 equals to ln of 435.48 minus T power 2 like this, times C. Okay, the laws of logarithms, when they are adding, multiply them. So we take A of both sides, this and this will go, we get A1 of T equals to this and this will go, get C times 435.48 minus T all squared like this. Okay, but we need to find this C, but we know that at T equals to 35.48 hours, A of 35.48 was equals to 500. So we just do that substitution, and so we will now have A of 35.48 equals to C brackets 435.48 minus 35.48 all squared equals to 500 like this. And so if we do this, we get C into brackets 400 squared equals to 500, and so C will be equals to 500 over 400 squared. And so if we use your calculator, 500 divided by 500 divided by 400 squared, 1 over 320. Okay, so therefore we'll have E of t for the second part to be equals to 1 over 200 into brackets 435.48 minus t all squared. So this is the model for the second part. Let me see. Okay, so oh, the question is really long. Okay, so determine the amount of pollution in the tank at any time t. We don't need to find anything again, that is all. So our final solution for the question become this, but we just have to rewrite this in terms of RVP format. So for the first part, we have this will look like a piecewise defined functions. So we know that at time from 0 from the interval from 0 to 35.48 hours, E of t was equals to 4,000 minus 3998 e power -3 over 800 t. Okay, and then at 35.48 going to t, okay, going to t, we have E of t to be equals to 1 over 320 over 435.48 minus t squared, like this. So you can then write your solutions like this, because there will be two for this time interval and for this time interval. For this time interval we have this solution, and for this time interval we have this solution. Thank you for watching. Kindly subscribe to the channel.